I'm going to talk about secrets in the ancient goatskin, Archimedes' oldest writings under X-ray vision. Uwe is a senior staff scientist at the Stanford Synchrotron Radiation Laboratory in Palo Alto. And I would say he's sort of living out the scientist's dream. The scientist's dream, you thought, was to get a Nobel Prize or something like that. But maybe the scientist's dream is to really hit on something or do an experiment or do a theory that really captures everyone's imagination, such that everyone around the world wants to hear about your work. And I think that's really the scientist's dream. And I think Uwe is living that out right now. I first heard about the Archimedes palimpsest in a PBS NOVA presentation about 2 years ago. I then invited a person who was featured on that show, Chris Rories from Drexel University, and an expert on Archimedes and his works, to give a lecture here in this colloquium series. And he spoke last year on a subject called "If Archimedes Had a Computer, Why Ships, Icebergs, and Buildings Topple." Maybe some of you remember that talk. Jan Hall in Boulder, one of our Nobel laureates, heard that talk and subsequently told me that he had heard Uwe Bergmann give a talk about the palimpsest and the use of X-ray measurements to interpret the writings. And he said it was the best talk he had ever heard. And if I had the opportunity, I should invite Uwe to give a talk in this colloquium series. And so that's how Uwe comes to us today. Uwe's undergraduate education was in Germany at the University of Karlsruhe and also the University of Hamburg. He did his PhD work in the United States at the State University of New York at Stony Brook, doing experiments at the Brookhaven storage ring. Subsequently, he did postdoc work at the European Synchrotron radiation facility in Grenoble and also at the Lawrence Berkeley lab. Before coming to Stanford, he also had positions at Berkeley and at the University of California at Davis. His research interests are basically the development and application of synchrotron-based hard X-ray measurements, hard X-rays being maybe in the 5 to 15 kilovolt energy range. The methods that he uses and develops are emission and absorption spectroscopy, X-ray fluorescence imaging, which, by the way, is the method that will be highlighted today in his talk, as well as various types of X-ray scattering experiments, both resonant and non-resonant. The methods he uses have been demonstrated and applied to a variety of targets or systems, for example, metalloproteins in biocatalysis. So he's got a foot in the biotechnology area, 3D transition metal compounds, water and aqueous materials, which is a recent interest of his, hydrocarbons and fossil fuels, and he's also been involved in measurements like you can hear about today on ancient manuscripts, fossils, and even brain sections. So you can see he spans a lot of applications and has a diversity of experiments that he's contributed to. In any case, Uwe has caught the tiger by the tail. He's been invited all over the world to give this talk, and I'm delighted that he was able to visit us from sunny California today. Would you join me in welcoming Uwe Bergmann?
This is the other one. I don't see my screen right now.
For those of you who came in late, got 3D glasses here. Some of the effects, if you would like to come up and get it.
Thank you very much for this kind announcement. I hope that that was not an exaggeration. Yeah, so please help yourself with the, I hope they're enough. If not, maybe you can share some of them. It's a great pleasure for me to be talking at NIST. NIST is one of those labs which, when I was a child, I already heard about it. It's a very famous place, and I think about it that's where you define really what 1 second is and what 1 meter is, etc. And it's a really true pleasure to be here. I should say one thing: the 3D glasses are not needed until the very end, and I will let you know when they are needed. So don't put them on quite yet. I wouldn't have thought, I mean, about 4 years ago, I would have never thought to get into this project, but I have to say it has been a lot of fun, and I really have enjoyed doing it, even though it's a little bit out of my normal type of research. This was the headlines on July 16, 1907, just about 100 years ago. In then called Constantinople, now Istanbul, the Danish scholar Johann Ludwig Heiberg discovered that in an ancient 13th century prayer book, there were drawings and writings from the Greek genius Archimedes. But let's start our story earlier than that. What you see here could remind you, if you live in California, it might remind you of the Sierra foothills on a sunny day. But in fact, it's the location where on September 11, 490 BC, the fate of Western civilization was hanging on a very thin thread. A huge Persian army had landed on the shore of Marathon, led by King Darius, and was trying to invade the Greek islands. The Greeks, after several discussions, sent Miltiades with an army of 10,000 Athenians and 1,000 Plataeans to the fight. They were heavily outnumbered, probably 3 to 1 at least. About a mile away from the battlefield, the Greeks formed their usual phalanx, meaning it looks like a turtle. They all put their shields up and slowly start to march. When they reached about 200 yards, just outside of the reach of the Persian archers, they changed their tactics into something which hadn't happened in ancient warfare until then. Rather than slowly walking into the hail of the arrows, they rushed down the hill. Some of them later said that they thought the Greeks had lost their minds. But what they really did with this ingenious attack, they completely surprised the Persians, got into an infight, and being much heavier armed than the Persians, they had at that point the advantage. The Battle of Marathon took a very short time. At the end, it is reported that 6,400 Persian soldiers were killed as compared to less than 200 Greek fighters. It was a complete defeat. One of the Greek fighters, with the name of Pheidippides, and that is a legend, was said to have run to Athens to report victory, and after which he supposedly dropped dead. The distance, some in this room might regret that Athens is so far away from Marathon. It was the first victory of a new form of a government, namely a democratic government. It was also the first victory of the Occident over the Orient. It was not the only battle. There were many battles before and after, but this is considered as one of the most important ones. And it marked the beginning of Western civilization and the age of classics. There were the great Greek philosophers. The first one, Socrates, famous for saying, "All I know is I know nothing." He was born just 20 years after the Battle of Marathon. His student, Plato, besides writing very important books like Republica, he also had a saying called, "Ignorance, the root and the stem of every evil." I think this holds today as much as it did over 2,000 years ago. And he had a student, Aristotle, who was by some considered the first scientist. He was very methodical about how he did his work. He also came up with this extremely famous saying, "The whole is more than the sum of its parts." He also happened to be the teacher of a 13-year-old boy with the name of Alexander, later known as Alexander the Great. And then, of course, there were the Greek mathematicians, Euclid of Alexandria. He is the one after whom we name our three-dimensional space, a concept which has held 2,200 years and was thought to be correctly describing our universe until Albert Einstein changed everything by suggesting that there's a four-dimensional space-time continuum. And then there was Archimedes of Syracuse. Without any question, the most influential of the mathematicians, and you can say that all of modern science has been based on concepts which were developed by Archimedes. He was born and he died tragically at the age of 74 or 75 years in the city-state of Syracuse in Sicily, which was a Greek city-state. He was sent to Alexandria to learn the teaching, to read the readings of Aristotle and also of Euclid. And he was not only a mathematician, he was an engineer, he was an inventor, and some would say he was a physicist. For example, he invented the pulley, a tool which is used today as it has been for thousands of years. We name after him the Archimedes screw, which is a pump system to pump water from a lower level to an upper level. And the same concept is, of course, used all around the world, even today. Those type of old Archimedes screws are still used in third world countries. And I think even some of the pumps in the car might be similar to that. During the siege of Syracuse by the Romans, Archimedes came up with a defense mechanism depicted here of a combination of hooks and levers, and it was used to shake the Roman battleships, sometimes from underneath. And it was reported that they were scared by this, and in fact, Syracuse was held much longer with that help, but eventually it did fall to the Romans. Probably most famous, and I should say this is purely a legend, we don't know how much truth is to it, is the Eureka moment of Archimedes. King Heros had a wreath, and he wanted to know, he had given that to the goldsmith to make him a wreath out of pure gold, and he wasn't sure whether the goldsmith hadn't betrayed him, so he wanted to find out how can we check whether this is really pure gold. And you can see that a wreath is such a complex object that is basically impossible to calculate the volume, even though you can easily measure its weight. And he went to Archimedes for help, and supposedly Archimedes, taking a bath, found the solution and was so excited about it that he reportedly ran naked through the streets of Syracuse. What Archimedes, of course, had figured out is that you can measure very easily the volume of any object just by dipping it into a liquid and then measuring the displacement of the liquid. One way you could have done this experiment then is you take the wreath and put an equal amount in weight of gold on a balance and dip them both in water. If they don't stay in balance, it means that the density of the one object has to be lower or higher. And that's reportedly what happened, so you can imagine King Heroes was not very pleased about that. Archimedes, and that is very important, he invented the law of the lever, very well known by our children. If you have two objects, A and B, with mass A and B, placing them at a distance A and small b, A times A equals B times B. How did he do that? I'll show you a very short and very beautiful, elegant way. Suppose you have two objects of equal weight, you put them at the same distance, they will balance, there is no surprise, and you can replace 2 by 4, or you can put the 4 in the center. This will always balance each other. Now let's say we put 16 on there, and we take 4 of them, and we replace them. We put a larger one in the center where those 4, where the balance is happy. Then you take the 16, and then you replace them, so you can put them, so you count 6, you go in the middle here, and put the 12 here. So you know that this, nothing fancy yet, this will always be in balance. Now all you have to do is go back to the old and count. Where was this center? This was 6 away, 6 units away, and then where was this one? This was 2 units away. Now you have 4 times 6 equals 2 times 12. That's the law of the lever. Sounds very straightforward, but it wasn't at the time. And even today, if you give this problem to a group, they tested that of high school students, say, can you show it very quickly? It's not that easy, just to ad hoc show that this works out. An extremely important law, which Archimedes has used throughout many of his proofs in his works. And I get back to that later. It also led to this legendary drawing and saying, give me where to stand and I will move the earth, which of course Archimedes would have never said, but it shows that the Greeks thought the earth was round, and it shows also that the law of the lever, of course, having, if you make one arm extremely long, you can move extremely heavy objects. Archimedes was the first to calculate the value of pi. Some people say that this was the mathematical equivalent of inventing the wheel. And I show you how he did it. This is, of course, the ratio between the diameter and the circumference of a circle. And he acted like I would say like a physicist. He said, I can calculate a triangle, knowing the well-known arithmetic or the well-known geometry laws, and I can take that as my first approximation. It's a bad approximation, but it's my start. So the circle has to be larger than the triangle. So let's do a better job now. Split each of those lines in half and then put in a hexagon. Now you calculate the hexagon and say, oh, this is a better approximation. So the circle has to be larger than the hexagon. And then Archimedes continued. He went to a dodecahedron. He went until 96. Calculated that number. And then he has a lower limit for the circle. But he wasn't happy with that. He said, I want to trap it also from the outside. So he started from the outside. You can start with the hexagon and then go downwards. You also go to 96. He didn't use the decimal system, but if you would use his numbers and present them in the decimal system, this is what came out. 3.1409, 3.1428. The more precise number is 3.1415. And as you can see, the lower limit actually is a little closer to pi than the upper limit. And if you look at the two examples here with the hexagon, it's not a surprise. The underestimation is a little bit less wrong, if you want, than the overestimation when you shoot out on the outside. A remarkable achievement by Archimedes, and 3.14 actually is the number which is often used in the construction business, and it's a very good number already. Now, we don't have any original writings of Archimedes that have survived. Archimedes wrote on papyrus scrolls, and his texts were written in one, basically all the writing was without a break, one line after the other on these long papyrus scrolls. And here is a famous drawing where you see him how he could have looked like when he was doing his writings. Subsequently, scribes copied the work on other papyrus scrolls until about the 4th century, when a revolution occurred in similar to something which we see today with MP3 data files replacing vinyls and CDs. They were starting to use, instead of scrolls, parchment, which is based on animal skin. And I have a piece of parchment here, which I will hand out. This is from the 19th century. It's an English parchment. This one is a sheepskin, and in fact we did our first test we did on this type of parchment. It is still produced. The parchment had two advantages. First of all, it's very indestructible. It is based on an animal skin, and it can endure very well. And second of all, you could bind it in these books, and then you can increase the density of storage with the books. What they used to write it is an iron-based ink. And not every parchment was written with this ink, but most of them. In particular, between the 7th or 4th and 12th century. Even today, this will, for example, which is from the 19th century, is written with an iron-based ink. The iron gall ink etches itself into the parchment and is very resistant and stays there for a long time. Three works of Archimedes are known to the world. Codex A, which was last seen around the year 1560. Codex B, which was last heard of in the year 1311. And Codex C, which is the subject of my talk, which was first discovered in 1907 by Heiberg. All of them were written probably around the 10th century on parchment. The reason why Codex C survived is because it was recycled, it was taken apart, and then reused in form of a palimpsest. Palimpsest meaning that you scrape off the original and you overwrite it, and then it survived as a prayer book, not as Codex C. And that tragic incident, if you want, was probably or most likely the rescue of Codex C, otherwise we wouldn't have heard of it. This is how you make a palimpsest. You take the original book, take out the leaves, try to take some lemon juice, some material, scrape off the ink as well as you can. In the case of the Archimedes palimpsest, you cut the large leaves in two, rotate them by 90 degrees, and then overwrite them with your new text. What you see here is that the old text, of course, because it was on the larger page and written in two columns like this, goes all the way through. So whenever you bind your new book, that old text will be very close to the edge. It will go through what you bind together. And that's a problem. And several lines of Archimedes' writings were lost because of this fact. Anyway, so you bind the smaller book, and then you have your prayer book. The ink of the top writing could be the same material, same ink, or could be another type of ink. In the case of the Archimedes palimpsest, unfortunately, it's the same kind of ink. So both the text underneath, the 10th century copy, and the prayer book text is written with an iron-based ink. What Heiberg had discovered in 1907, and that's why it made headlines around the world, was that in this prayer book, he found the only surviving Greek version of Archimedes' probably most famous work on floating bodies. All we know, or all we knew about on floating bodies was based on a Latin translation from one of the other codices. He also discovered two new treatises. The Stomachion, an ancient game, which Archimedes was obsessed with. Very fascinating. You can look it up. It has, I think, 20 triangles which you can put in a square form, and there are more than 14,000 combinations, and Archimedes figured out actually how many combinations there are. And probably most importantly, the method of mechanical theorems, a treatise by Archimedes which was incredibly advanced. Some argue that this was an ancient form of calculus. Now, Heiberg was not allowed to remove the prayer book from the Metochion in Constantinople. So what he did is he photographed it and then went back to Denmark and transcribed it based on his photographs. And between 1910 and 1915, he published the complete transcription, which did have a lot of holes because of the fact that he used, of course, a probably dark room where he made his copy, and also to some extent that he had, when he was reading the text, the mathematics, that he had used assumptions which were holding in early 20th century, and he was also not a mathematician. So we have the Heiberg photos, but they were incomplete. Now let me tell you a little bit very briefly about the method of mechanical theorems. Archimedes wrote that as a letter to his friend, the famous Eratosthenes, and you at NIST might really appreciate him because he was the first to measure the size of the Earth. And this was done about 200 years BC. He knew that in Aswan, which lies exactly on the Tropic of Cancer, on the summer solstice, the sun is perpendicular to the horizon, or basically there's no shadow. And he also knew that on the same day, at the same time, in his hometown Alexandria, there was a 7.2 degree angle of shadow. What he had to do is figure out the distance between those two places, and he knew that roughly from the caravan travelings to be about 5,000 stadia, one stadium being 180 meters roughly. Now you have the answer. 7.2 to the green distance equals 360 to the circumference of the Earth. Eratosthenes' value corresponds to about 39,700 kilometers. Now the error here is mostly based on the fact that we don't know exactly what one stadium is, and maybe there wasn't even an exact definition of one stadium. It's a remarkable achievement, and to me it's even more remarkable that the great Columbus, when he landed on the shore of what is now called America, thought, he was completely convinced, in fact, that he had landed in India, which is about 3 times further away. He did not know the size of the Earth. Or at least, if he knew it, he pretended not to know. I read that he never knew it. This is the letter of Archimedes to Eratosthenes. Greetings, since I know you are a diligent and excellent teacher of philosophy and greatly interested in any mathematical investigation that may come your way, I thought it might be appropriate to write down and set forth for you a certain special method. These are the first words on the treatise, The Method of Mechanical Theorems. And then he goes on, I presume there will be some among the present as well as future generations who by means of the method here explained will be enabled to find other theorems which have not yet fallen our share. Let me give you an example of the method applied to calculate the volume of a paraboloid. So this is a parabola, and if you spin it, you get a paraboloid. Archimedes, and this is one of the most simple examples you can use, used his method to calculate the volume of a paraboloid. What he did was very beautiful. He said, well, we know if we have certain distances, for example, we know the distance BD, we know the distance OS, we know the distance MS, AS, and AD. We can, because in general you can just say x equals y square, there are some very general and simple relations. So for example, BD square divided by OS square equals AD, so BD square by OS square equals AD divided by AS. So that's very simple. That's just, you don't put in anything other than knowing that this is a parabola. And then you change these equations to make it in this form, and you insert the number pi on both sides. And what you can then say is, if you have a circle, or let's say a shaped, like a little circle of this area, pi ms square times the distance as here, will be the same as if you take an OS square times the distance AD. And now you're back, you can go back to the law of the lever, because you can do now something. You can say, let me take an ms square circle, or let's say an ms square disk, and an OS, pi OS squared disk. The one I put at AS, the other one I put at AD. So D and H is the same. So I put it at this thing, and they will balance each other. Very straightforward. Nothing, you have put nothing in yet. And now I do the same thing again and again. I take a smaller one, and that will balance the large disk closer in just by using that equation. Or I take a larger one, it'll balance the other disk here, and I fill up my whole cylinder with disks. And here, in an imaginary way, I put all those disks at the same location H. Now, in practice, I cannot do that very well, but what I can do is I can place them then like this. So I keep the center of mass, so I stable them all up, and then I fill the other disk this way. Now you have kept the balance. You have used nothing else but the formula for the parabola, and you have the solution, because the center of mass of this is very simple. It's just half the distance. So the volume of the paraboloid is half the volume of the cylinder which encircles it. This is using Archimedes' method of mechanical theorems to solve this. And it can be used to many geometrical objects. What is significant about the method, and this is just coming to light in the last years, actually since the palimpsest had resurfaced, it's a geometrical discovery with a physical thought experiment. Very opposite than what we do often today. Today, often we do physical experiments with geometrical thought experiments. It also was a breakthrough comparable to modern integral calculus, because he used infinitely many little disks to fill up his paraboloid, for example. And some have argued that both findings are essential features of modern science, and that the method was 2,000 years ahead of its time. There's a lot of speculation. What would have been if, in the Renaissance, Galileo or Da Vinci or even Newton later would have had that information, would have known about Archimedes' method? Would science be at a different state today? I think we will never know the answer, but it's a lot of speculation about that. They didn't know it because at the time, Codex C was in a prayer book in the Holy Land in the San Sabah monastery. Now, after Heiberg had taken the photos, it had disappeared, and that was right after World War I, and it was thought to have been lost. And then it resurfaced in the 90s. 1998, it was sold at Christie's for an incredible amount of $2 million to a private owner who reportedly pledged not to limit access to an ancient manuscript. This was incredibly important. And none of the work which has gone on since and which I'm showing today would have been possible without this pledge. So we are very grateful to the owner for that. He was contacted by the Walters Art Museum, not too far from here. Go there for a visit. It has a remarkable collection of ancient documents. It's in Baltimore downtown. And he agreed to lend the manuscript for an integrated effort of imaging and conservation. And this effort is still ongoing. Now, this was some of the problems. Here you see a photograph of the first 2 pages of the Archimedes palimpsest in horrible condition, much worse than when Heiberg had seen them. But even Heiberg hadn't seen those pages very well. They seem to be even a little bit burned here on the edges. And whatever little reading you can make out is not the Archimedes text, it's the text above, it's the prayer book text. There was another problem. 4 of the leaves had these medieval miniatures on them. And at one point they were thought to be maybe they are part of the original prayer book, but it was found very quickly, actually, that they were forgeries which were put on after, we know now they were put on after 1939, actually. And we have no idea whether we think that the person or the group who did that did not, of course, know that they didn't just deal with a prayer book, which they wanted to make appear more valuable. We think that's what we think they thought. They had no idea what they had in their hands. St. Luke, the 4 evangelists, underneath on floating bodies. St. Mark, underneath on floating bodies, equilibrium of planes. Double bifolio, an original full leaf. So we call those bifolios because that in the original 10th century, that was 1 leaf. And then only in the palimpsest, it was put together as 2 leaves. So it's 64, 57. R is always recto and verso. St. Matthew, St. John, underneath method of mechanical theorems. Incredibly important text underneath here. And as you can see here, the pages were deliberately mutilated. This is not decay. This is someone cutting things out with scissors. It's way too straight to be just decaying. The person wanted to make these things appear really very old. Now, you have seen it. X-ray vision is one possibility to look under these forgeries or to look under these texts. And of course, as you know, the true Superman is Wilhelm Conrad Röntgen, who in 1895 took the first X-ray image. And you can see the size of the jewelry at the time. It has X-ray, this type of X-ray imaging has revolutionized science. There's no question about it. Independent of the other fields of X-ray research which has been going on since. There's no one in this room who hasn't had multiple X-ray images taken. You could also say, what is if we, and that's of course the most obvious thought, let's just take an Archimedes page and put it into an X-ray machine and then see what we get. And I can tell you, not that we tried it with an X-ray machine, but we tried to get a transmission image like a normal X-ray image is. It's a transmission image. You measure how much the different density absorbs. You will not see anything. You will see sometimes something if the ink is still very concentrated. But for dilute ink, for thin ink, with the normal transmission X-ray, you will not see anything. The contrast is too small to see it in a conventional X-ray. Now, I don't have to tell you about X-rays. They're part of the electromagnetic spectrum, and the only difference to radio waves and microwaves and infrared and ultraviolet is that they're in the very high frequency range. Typically, you can say typically starting at 10 to the minus 8 and then almost to infinity to short waves. There were two very important experiments in terms of X-ray imaging, or actually one in X-ray imaging and one other one. This was a science paper by Horowitz and Howell in 1972, a scanning X-ray microscope using synchrotron radiation. And what they showed, they imaged a 2-micron whisker of silicon. And they report in their image, they say, the result indicates the importance of detecting fluorescence re-emission rather than transmission. The signal is much better if you do it not in transmission, but if you do it in fluorescence re-emission. Another important paper, and I'm glad to say that one of the authors is actually the late Mel Klein, used to be a friend and collaborator of mine, is that the fluorescence detection also helps you when you do spectroscopy on very dilute systems such as metalloproteins. Okay? And this is now one of the absolute landmark papers where they used it to show fluorescence detection for XF, that the signal is so much better when you do it in fluorescence rather than in transmission. Now, I'll show you very briefly the basic idea of an X-ray fluorescence. If you have completely simplified the inner workings of an atom with the nucleus and the electrons are bound to the nucleus depending on what number of protons you have in the nucleus. The larger, the stronger the inner electrons are bound. And every element in the periodic table, because of that, has its unique X-ray fluorescence fingerprint. You come in with an X-ray, you knock out, let's say, an inner electron. It's filled from an outer electron instantly and then emits a fluorescence X-ray, a secondary X-ray. And the energy difference between those two orbits defines the energy of that re-emitted fluorescence X-ray. And therefore, every element has its unique fingerprint or spectroscopic fingerprint of X-ray emission lines. So if you want to now look at iron in the ink, in that case, what you do is you tune your detector to just measure the spectrum of the iron fluorescence, or the narrow range of energies from the iron's fluorescence, and you do the imaging. You can, of course, no longer take the whole image with a plate behind. You have to use a small beam and scan because the fluorescence loses the information where the X-ray came from. This shows you now a spectrum of the taken from the Archimedes palimpsest, and you can see some of the lines. This is the iron line, the K alpha line, and this is the iron K beta line. There's a little bit of manganese, lots of calcium. That is mostly from the parchment, but there's also some calcium in parts of the ink. And what you then do for the imaging, you say, okay, I'm going. In fact, you can set several windows on your detector. We set up to about 5 windows. You said, I'll set a window on iron, I set a window on calcium, and then maybe one on manganese, maybe something on copper. And you set those windows and you record those elemental spectra as you go along. And the experiment, conceptually very straightforward. You take a small X-ray beam detector, you scan. Each time you hit this element, it'll give you a signal, and you just raster through the whole thing. In order to get an image from one page of the Archimedes palimpsest, you need about 15 million measurements. And that requires not only a very powerful X-ray beam, but also it requires a system which can measure very fast. Otherwise, there's no chance that you can get such an image in a reasonable amount of time. This is a place, of course, where you get powerful X-rays, the Stanford Linear Accelerator Center, in particular the Stanford Synchrotron Radiation Lab, which is in this conglomerate of pretty old buildings, but updated with a new ring, Spear 3, a powerful machine today. And it's one of the many synchrotrons. I'll just show you some which are operating around the world. There are about 70 around the world of all various sizes. This is the largest in Japan, Super Photon Ring 8. It's so large that they didn't find a flat area, so they built it around actually a little mountain. The advanced photon source in Illinois, across the San Francisco Bay at Lawrence Berkeley Lab, a smaller ring, the advanced light source, the European Synchrotron Radiation Facility, Berlin. I'm just showing some of them. Typically, the new rings are all in the 3 GeV range. These are the most powerful. These are the largest ones. These ones are as powerful, but they're more optimized on softer X-rays. So the large rings are more optimized on hard X-rays. The smaller ones more on soft X-rays. The new generation of X-ray synchrotrons, which are just now starting up, like Soleil, Diamond, and also the planned NSLS2, they will be all like Spear, operating about 3 GeV energy. The concept is straightforward. You have X-rays in the vacuum ring, and then you have bending magnets which send out a fan of X-rays, and you have ondulators and wigglers which send out a very narrow cone of X-rays. Very powerful. In fact, the brightness, which means the intensity focused into a small area, collimated into a small area, in a small spectral range per second, is not just 1 million, it's brighter than 1 billion suns. You can see here 10 to the 10. Now the new ones are going up to above 10 to the 20, actually. This is the brightness of those things. They are polarized and they're tunable, and they're short pulses. For this work, we take advantage of those 3 properties. We don't take advantage of the short pulses, which is done in some other experiments. This is a quick inside look of the new Spear 3 ring, and then the lab is on the outside. You can imagine, when I joined this project, I wrote a proposal to the team saying that I want to use a synchrotron to image the Archimedes palimpsest. And when the owner heard that I'm using a beam which is 1 billion times brighter than the sun, he was very pleased about that. And so, of course, he wouldn't just send us the book. We had to start to do some tests. And the parchment which I just handed around was exactly part of these tests. This was our very first image we ever took at SSRL. This is the writing of the word "or." I have the little snippet in my bag. It's the same kind of it's the same handwriting as what you have seen. And it was done with a 40 micron pixel size. 40 microns is about 600 dpi, 600 dots per inch. And you can see very quickly that, and this was just a very fast scan, you can see that in principle that the method works. And after coming up with numbers, and we did some radiation damage tests on some parchment, where we exposed the parchment to different doses of X-rays, and then established a safe dose. After that, after I also convinced the team that I can get a 50% humidity and temperature stability inside the hutch, which was a pain in the neck, finally the team decided to come and bring one page first, and then they came with more pages for testing. And here you see Abigail Kwan. She's the senior conservator at the Walters Art Museum, and she was the only one allowed to handle the palimpsest. She's just putting in one of the forgery leaves into our beam. And I'll show you a little bit the closer setup. This was an early picture. Now things look a little bit better. That was still when we used lead tape and C-clamps. But the important thing is probably just two things. At the end of this pipe, there is our slit, which was a 50-micron pinhole. So that defines the size of the beam, and the beam was pretty much collimated. And we also look with a detector at a 90-degree angle, and the 90 degrees are very helpful because it reduces the scattering. It uses the polarization of the synchrotron of the X-rays, similar to your polarizing sunglasses when you look from the glare scattered from a water puddle. And it suppresses the scattering. We are not interested in the scattering. We are interested in the fluorescence. The fluorescence has is not affected by the polarization. It goes into 4 pi, but the scattering at 90 degrees, it's basically the X-ray Brewster angle. The Brewster angle for X-rays is basically 90 degrees, and so you can reduce the scattering dramatically if you look at 90 degrees. All fluorescence measurements at synchrotrons are done at a 90-degree angle with the polarization of the synchrotron in this direction. Now let me start to show you results. This is the bottom part of page 1 of the Archimedes palimpsest. It is the page where the monk who had used the pages from the original writings and reassembled them into his prayer book, where he had dedicated his work. It is called, in the scholarly community, they call it a colophon. He writes down the date, the name, and sometimes the church to which the work is dedicated. We were our colleagues with multispectral imaging, which is an optical method which has been very successful, applied at this project, they were able to come up with a date, but no one knew the name of the scribe. This is now the X-ray image. This is the iron X-ray image of that same part, and these are all writings by the scribe, the monk, and this is ancient Greek, by the way, but these fancy characters, that is his dedication. And when you read it, it says, this was written by the hand of Presbyter Johannes Myronas on the 14th day of the month of April, a Saturday of the year 6737, which corresponds in our calendar to 1229. It was the day before Easter. He had just finished his work, and it took 666, I think 777 years, if I'm not mistaken, yes, 777 years before his name was finally revealed with the X-ray image. But of course, as interesting and as important this might be, or is actually, to those who look for other palimpsests, to find out his name, and then maybe find other works by him to look for other palimpsests, we are really, most people are really interested in the Archimedes writings, and now I show you the full view of this page, and this is the full X-ray image. You can see all in this view, all the Archimedes writings are horizontal, and the prayer book writings are vertical. So this is now a flipped. This was the section I just showed you. So this is now a flipped version. So the Archimedes writings are horizontal. We also found another interesting thing. There was a hand, as you can see. It's basically like this. This was Johannes Myronas. He had done a little drawing on that first page, and no one knew about this drawing. But more significantly, this contains the final proposition, not the complete, but parts of the final proposition, the most complex of any propositions of Archimedes' work on floating bodies in the original Greek. And when we got this image, my colleagues, we had a team of at least 8 people all the time, and they were working very fast the images come in, and there was a data processing going on very quickly. They were transformed into these kind of images from the, let's say, the ASCII file of the numbers of counts, and sent out to the scholars. And at half an hour past midnight, after we had just sent it out a little bit earlier, we already got the first reply from Revil Netz. He's a Stanford professor who is one of the eminences on Archimedes. He wrote this email back to us. Column 1 on 1F, 1V, that is the first page, versus is sensational. I attached the transcription of lines 2 through 11. Previously, with very hard work, I squeezed some 3.5 lines out of the old pseudo-color, but now I fairly easily read effectively the entire text, noting a couple of errors too in my old pseudo-color-based reading. What Revil had seen is that we found a different arrangement of some of the diagrams and some quite significant differences to the Latin translations of what was known until then of this final proposition. This is on floating bodies. And this is the first time in modern times anyone has read this text in the original Greek. I told you that the pages were originally one page and then basically cut and then bound together in the book. Some of the pages were actually ripped out. And all we had left is some of the ripped out pages. One or two are missing, but what we had left is these stubs, which were when you rip, it's like when you rip out a page of a book, then the stub stays in. And we had also the pages, but we didn't know which stub belongs to which page because you cannot see anything on the stub. This is the normal visual appearance of such a stub. This is the multispectral pseudo-color image from our colleagues from Rochester Institute of Technology. And well, you get this one out a little bit better, but you still don't really see much. And this is the X-ray image. You can read it straight away. And we had about 15 or so of those stubs, and it took literally only seconds. This is an ancient omega, by the way, which looks like the infinite sign. It literally took very few time for the scholars to then reassign those stubs to the corresponding pages and then finish the transcription of those pages with these stubs. There was another surprise. This is on folio 159-58. This is now in the middle of this bifolio. So it's the part where the book was bound together. And there was a little drawing. It has the method on it, very important. There was a little drawing here. This is already a pseudo-color image. The visual image, you see nothing, was brought out very nicely. But there were some debates about some of the labels. Here you might see a lambda. There was a mu here. Heiberg said there was a mu here. In the calcium image, that was a surprise to us. We brought out the full image all of a sudden. No one had seen that before. Why in the calcium image? Because we always thought that there was more actually iron in the ink. But in this particular case, we think what had happened is, now here is a photograph of this area. We think what had happened is when the image was drawn, it was basically the nib pushed it in with the ruler, it was pushed in. And then later, when the ink was removed, the chalk of the parchment collected in these grooves and formed a thin layer of calcium, more amount of calcium than in the rest of the parchment. That's what we think. We don't know it precisely, but we were happy that in the iron image you don't see this, but in the calcium image you could see the full diagram. And we also settled a long-standing dispute about one of the letters. That was done with the iron image, by the way, between whether the label which Heiberg said was a mu or which Revil said. He said it would only make sense to him if it's a nu, and it turned out to be a nu, so Revil Netz was very happy about that. Now let's go to, this is one of the important forgery pages, which has the method underneath here. You get the normal view. This is the X-ray image. We ended up doing those forgeries actually from the back side. The parchment doesn't absorb much of the X-rays, but the metals in the ink of the forgery, they absorb quite a lot. So in basically all cases, what we did is we shone through the back side, and then we get, of course, both sides, which you see here also. And then you flip the image, and then you can read the text which is really on the side of where the forgery is. And here I give you an example. So these writings here are on the back side, and then the little bit fainter writings, those ones are on the side of the forgery. That's why I show this image already in reverse. And so I zoom in here. So this would be Archimedes writing on the back side, not on the forgery side. This would be Archimedes writing on the forgery side. And the X-ray images were quite, I would say, I mean, not sensational, but they're very, very helpful and impressive to bring out all these texts. Not everywhere, as you can see here. Unfortunately, in this area, there's so much iron in the painting, in the forgery painting, that the signal, you can see a little bit of text here, but in some area right here, it is basically, with this kind of image quality, it's basically not possible to read everything. In some cases, calcium helped us in these areas as well. But what was shocking to me was that after having sent all this beautiful image to Revil Netz, that he said, well, what really struck me is this area down here. And now I blow it up for you. This is now this area which I just pointed at. The parchment ends here. This is the end of the parchment. Everything you see below was some parchment added later to it. So there's no information here. The real information is here. And here now comes Revil Netz, scholar, and he reminds me very much of the way how we do work. He says, okay, this one, you can see it here, this one has to be a kappa. And then, of course, in all fairness, he knows the rest of the line. So he can already exclude a lot of words which don't make sense. This one is an alpha. And now comes the real one. You can see this thing here. It's an iota. In fact, it's an accent graph, and the only Greek letter which has such an accent is an iota. So the word is kappa alpha iota, and it means the word and, A-N-D. The line has to continue here. Heiberg had thought that this was the end of a line. Revil had now, basically with this one word, had established there were 2 lines of text missing. The whole transcription of Heiberg was based on 1 line of missing text, and that changes everything. Let me just give you again his comment. The chi at the end is very safe because while the alpha is almost entirely gone, the iota is entirely gone. The grave on the putative iota is clearly visible. There are very few alternatives to the reading chi, which in context is also quite likely. The finding is significant for the debate of Archimedes on the concept of infinity, which he discussed very early in the method. In the Heiberg transcript, and I cannot go into much more detail because it's a delicate issue and I just don't know more about it of what I tell you now. Heiberg transcript, he argues that Archimedes used a logic saying if it is true for any line or if it's true for any number, it is therefore true for all. Whereas now based on the X-ray image, Revil says he thinks that Archimedes had argued very differently, that he had argued in a sense that not for any, but however many lines are taken, if I can take however many lines I want, I can therefore take infinitely many. And it's a different way of defining or conceptualizing infinity. This is an ongoing debate, and I think we will have to wait a little bit before this is really settled. Now let me show you some stereo images. My colleague Bob Morton, he suggested to use stereo image. Before I put on the glasses, I'll just show you the way how we did it. It's very straightforward. All you have to do is, so this is, let's say, the 45-degree angle. And then if you take the point where the beam hits the parchment and you rotate it, you rotate your parchment by 7 degrees, and then take the image again. Now 7 degrees is a good number because, yeah, I'll give you mine. 7 degrees is a good number because 7 degrees is about the angle of your eyes when you read a normal newspaper, unless you are really short-sighted or far-sighted. So that's about 7 degrees. And so you have to put them on. The red goes to the left eye. I hope it should be straightforward. So the left goes to the red eye. And now let me invite you to the inner of some of the Archimedes parchment. This is, you can probably make out that this text looks to be like floating above, and then some of the text the horizontal text is below. I'll zoom in a little bit more. I hope it comes out clearly. You can get a feeling of the depth of this parchment by looking at it with this stereo view. I don't know whether it's good to turn down the lights for this one a little bit. Yeah, I'm just giving sign to the... So you're having basically now, you can also see how wavy the parchment actually is. It's not flat. And this kind of a stereo view image gives you a hint of that waviness. I'm zooming in a little bit more. So now you can see it again. The vertical letters are really floating there from the front side of the parchment. And then some of the horizontal, the Archimedes writings, are well below the parchment. And all the rest you see is some residue iron which was distributed in the parchment during the process of trying to erase the text, or maybe some residue iron which was just left in the goatskin. So these are the stereo view images I have left, and keep the glasses. I have one more a little bit later. And I would like to use that image also to end my talk. We ended up not using this technique for many of the slides because the scholars were quite happy with the normal view. They didn't really need the stereo view in order to do the reading better. But it could have been done, and in some cases it will be maybe done in the future. It takes, because you have to do the two angles, it just takes twice as much time. And it's very easy actually to produce those images afterward. So let me just conclude with an outlook. The project is pretty much finished from our point of view, from the X-ray imaging point of view, but there's one small part which the scholars still want to revisit, and it's part of the stomachion, which is that ancient game. And Reviel Netz in particular has insisted that the collaboration should come one more time to SSRL to image that. The reason why we haven't done it yet is it's on an incredibly damaged page, which is hard to, I mean, you don't even want to pick it up in your hands. So we have to come up with a very safe, because we have to put the page, we don't image horizontally, we image vertically, because otherwise we would have to deflect the X-ray beam, which is very hard to do efficiently. So we have to hold it in a safe way vertically. I don't think it's a big problem, but they have been a little bit reluctant to that. They promise they'll come, not next year, but in 2009. Let's hope they do it. And of course, there will be a full translation available. This work is ongoing. There will be larger publications with small parts to it. For the X-ray part, I'm working on a longer paper right now, Review of Modern Science, to describe a little bit more the X-ray fluorescence technique. And of course, there are, in this large publication, which is, I think, at the Royal Society publication, there will be, everyone will be brought in, the conservators, the scholars. And the scholars, of course, have the main say, because that is really the significance, as well as the imaging experts. The palimpsest will be on display as well. We do not think it will ever be re-put into the book form. So the pages will probably stay separate as they are right now. There are 174 pages. And an exhibition is planned. Last thing I heard is most likely will be at the Field Museum in Chicago. I don't know whether there's a chance that it might happen at the Smithsonian or something, but I think that's what I heard. That's what they plan to do. And I don't know the date. It might be next year. It might be sometime later. A new book just came out by Netz and Noel called the Archimedes Codex. If you like a scientific detective story, I think it's a great book. It is written in a very, I think, in a very good way and very entertaining way. My colleague Reviel Netz and I, we have been playing with the idea of an Institute for Imaging of Human Heritage at Stanford University, and we are basically at the point of a white paper which we have submitted to the Dean of Research and have them have a look at it. It'll still might take some time, but there could be a large interest in using not only X-rays, but other techniques, other advanced techniques, to look at some of the thousands of old parchment documents, including many palimpsests. The work has also, and I'm very happy about it, has inspired other research. And Bill mentioned it at the beginning, brain imaging. We have started to look at Parkinson's, Alzheimer's disease, slices of brain, large slices, full size. X-ray fluorescence imaging has been along for a long time, but no one has really applied it to large objects because of the fact that you need to do it very fast. 3 milliseconds per exposure time, or 1 millisecond per exposure time, measuring on the fly. So that is the new thing, and that came out of the necessity of imaging these full pages. The resolution is not that critical. We don't need like the world's best resolution, but we need to do it fast, otherwise we cannot look at large objects. And also fossils. And I will show you now, if you put on the glasses again, this was a fossil image taken of a 122 million year old transitional fossil between a dinosaur and a bird called the lioning bird. And it's not a large effect. The X-ray view comes out just a little bit because it's not doesn't have much depth. And the X-ray image shows you the feathers. You can see the feathers on the side of this bird, and you can see the bone structure. We are creating those fossils with looking at different elements at the same time, and then use the different colors for the different elements to bring back the fossil. Now, the interesting part of this particular bird, this was found in the Gobi Desert in China, is that we think that this is the heart. And I'm going to zoom in now a little bit. You still have your glasses on. This is now like this chest section of this fossil, and the heart would be, I hope you can see it, the heart would be in this area here. Why is the heart so important? It is because dinosaurs were not warm-blooded. They were actually cold-blooded. Whereas we know that birds' flight requires so much energy that it's very likely that the early birds, and even those dinosaur-related birds, probably must have been warm-blooded. And in March next year, we will get the Archaeopteryx, which is a very famous fossil, and we will get the best specimen of that to SSRL and to try to take an X-ray image of that. So this is just another research, and let me now thank my collaborators. It's a great group of people from different places. I don't want to mention everyone by name. At SSL, Martin George had been wonderful, and then Will Knoll, he's the project director at the Walters Art Museum. He's a very good friend and great person to work with. And we particularly thank, of course, the owner for being very generous in lending us this book and also supporting some of the costs for the team, not so much for us, but for the team. And of course, the Department of Energy, SSRL, and SLAC. And I will end by just showing you a couple of impressions of what was going on the beam. And thank you very much.
Thank you, Uwe. That's a fascinating story, and I hope you all enjoyed the special effects of the 3D. And please leave these up here on the stage as you leave, and I hope the parchment comes back too. We have time certainly for questions, and if you would use the microphones, we'd appreciate it. I had one question myself. When we looked at these images, was the monk also using iron ink? So we were looking at a superposition always of the monk's writings and
right.
Were they in the same language? Were they
in the same language? But as I pointed out, they were at 90-degree angle.
Oh, so that was
key. Yeah, that was very important. There were some overlaps, but also which comes out maybe in the let me just go back quickly to the, and I will come back to. In this image, you can see that with the X-rays, because they are not like an optical probe. If you look at here, so now this is the monk text here, and then this is the Archimedes text underneath. Yeah. You can see at the intersections, the iron signal adds up. And so that means even though there is text above, it does help you to know whether is there anything below or not. So here there's nothing below, and then here is clearly from this Archimedes letter, this is below. So yes, it is a mess because you have actually 4 texts. You have the front side, the back side, and you have 2 inks. But it is possible, or has been in most cases, it has been possible to still read it, even though it's both with iron ink. Yeah.
Okay. Another question was the incident light white light, or was it somehow resonant with the iron?
The incident light was chosen such that we used 8 keV, which is just above the iron. So it was not quite resonant. We wanted to keep the elastics getting away, but it was specialized on iron.
Okay.
And then at one point we were looking at some heavier elements, so we used higher energies, right? And at one point we only wanted to look at the low energies, so we went below the calcium edge actually, because there's a lot of calcium, and looked at some of the sulfur and the very light elements. But that was very hard because the cross-section is so small for those.
Okay, question?
I have two quick one. When was the Archimedes' text transcribed?
Yeah, this particular text is, I mentioned that shortly, this particular text was believed to be transcribed around the year 950, okay? And of course the obvious question is, how close is it to the original writing? And the scholars believe from using different methods. Of course, we don't have any original writings, but you can use different methods, which are also sometimes used in DNA when you do some dating of how changes in the DNA occur. And with text, they use similar algorithms. It is believed that it's a very close translation to the original. Probably it was the fifth copy, so the fifth generation of copies. And it was different in the sense that it was not written in one word, as Archimedes did. It was written in pieces. We also know that the scribe, the scribe, whom we don't know who he is, who translated or who copied that, was not a mathematician. He knew nothing about mathematics because he did some very, simple errors which a mathematician would have not done. Now that was a good thing, because there's nothing worse than getting a guy who thinks he can edit the writing of a genius, because you cannot edit the writing of a genius.
I have also a technical question. Is it possible at all to somehow get a depth dependence by
confocal imaging? Yeah. There's a team at Cornell which is trying that. I don't think it will be realistic just because of the time scale involved. You need so much more time to do it. Because, see, if this parchment would be perfectly flat, you could say, okay, so at this height we have it, and we just go to this height, and then all we see is the text underneath. But in reality, the parchment, as you've seen, is wavy, and you would have to realign almost for every little step. You would have to realign your confocal beam, and they are trying it. I don't think it will be very helpful. I also, to be honest, I also don't think that part is really the biggest problem. The biggest problem where the X-ray fluorescence failed, and obviously I didn't show much of those examples today, is the fact where there are really some parts where there is no ink left. Okay, and there are also some parts in other writings in this book where they used a slightly different ink. So that was actually our biggest problem. Once you see the ink, in most cases you were able to somehow disentangle it.
A question here on the right, and can you turn up the volume on the aisle mics? Thank you.
Have you considered the use of laboratory-based non-synchrotron X-ray sources, for instance, commercial X-ray fluorescence units and that sort of thing?
Yes. In fact, my colleague Gene Hall, who is not far away from here, he has used, he is here from Rutgers. He has done the very first tests with a commercial X-ray tube. Like there was an EDAX machine. It works. You can see the text, but it doesn't work because it takes way too long. It took about 8 hours to get one letter with low resolution. So you do need the incredible brightness and intensity of a synchrotron. You do need to do it extremely fast. 15 million measurements for one page. It's 8 hours if you do it with 3 milliseconds. It's 8 months if you do it with a laboratory source, and that's just not viable. Plus, it's not polarized, so you will always get more background. Plus, it's a Bremsstrahlung spectrum in addition to the characteristic line, so you will always get background also from the Bremsstrahlung of the X-rays. So the quality of image, no matter how you do it, even if you tune, we did not use the full intensity which you can get at a synchrotron, right? You can get 100 times stronger than what we used. We just used as much as we needed to not saturate the detector and to image as fast as we could. But the fact that you can tune the X-rays at your will and you can do it very quickly and that they're polarized is just such a tremendous advantage that it's worth the trouble to travel to the synchrotron.
Yeah. Okay, question here on the left. Yes.
You mentioned that you never would have imagined being involved in a project like this. Will you talk a little bit about how you did come to be involved?
Oh, well, very, very good question. Thanks. It was a complete coincidence, as you call these things. I was at a conference in Germany on photosynthesis, and it was a short conference. We spent all the time, and a lot of my work, ongoing work, is we look at very dilute systems, like in that case spinach, and spinach has, of course we all know, has iron in it, but it also has the manganese in it, which does actually the splitting of water, one of the most important chemical processes on Earth, actually. Splitting of water and emission of oxygen, which trees do. And before I was flying back to the US, I stopped at my parents' house in the Black Forest, and my mother, she had put like a staple of things on my desk, basically, which mothers always do. So they give you all these things which you should read. So just read those, look through them. And there I found a magazine, a German magazine called Geo, which had an article about the Archimedes palimpsest in there. And I read this article, and I found it fascinating because, you know, Archimedes is a fascinating character, and it was a fascinating article. And I think it was when all of a sudden I read in this article, I said, and the iron gull ink, and an iron gull ink was used. That's when I said, wait. That's when it struck me. I think if they wouldn't have used the word iron, it just might have slipped through. At that point, I said, we should be able to do it because we look at manganese in leaves, and iron in leaves, and that has to be more difficult than looking at the residues of iron in an old page, right? And then the rest was just to use the same detection method, namely X-ray fluorescence, but not doing a spectroscopy with it, but doing imaging with it. And X-ray fluorescence imaging has been around for a long time. So in the morning I went down to my mom and said to her, "Look, I think we can do that. That should be easy for us to help to look through those texts." And she said, "Of course, sure, right."
You didn't say eureka.
No, I did not.
Are there any questions from Boulder? We don't have a picture of you, so if you have a question, just speak up and interrupt as we go along. Yes, another question?
Well, I wanted to know, so then did you just call up the museum and say?
Oh, right. So that was just the beginning. So I sent an email. I flew back, and then, you know, the thing sits on your desk, and you have other things on your there. And I think I have all the dates still. I sent an email to Abigail Quandt, and I got, within the day, I got a response from Will Knoll. And I said, you know what, I think I have an idea how to do it. And then he said, well, send us a short proposal, because he said, we get hundreds of ideas, basically, literally, and send us a short proposal, like kind of a one page. And then after he read that, he said, well, why don't you come in April? That was April 2, so I sent it in November 2003, and then April 2004, why don't you come? We have a workshop, because we are at a stage. So the timing was really perfect. We are at a stage where all of the methods we are using, in particular those optical and ultraviolet methods, are coming to kind of their limitations. And we are looking for new methods. Why don't you come and give a short a half-an-hour presentation, and then we will decide, so there were other people, we will decide whether we can use one of those techniques. And it was at that conference, at that workshop, it was a workshop on April 1st of all days, 2004, where I also met with my colleagues who had suggested independently to use a laboratory X-ray tube, and I suggested to use the synchrotron, and that's when everything started. And it took us about another 6 months to do all the tests, besides all my other work, and then a year later, basically, a little bit less than a year later, they came with the first page. So it was, I have to say, it was incredibly unbureaucratic. It was very, it was wonderful, because no one said, no, you can't do that, you shouldn't do it. We just did things on the side. We didn't bother anyway. We just started to do things on the side.
I have a question from a conservator point of view. Nowadays, for ancient documents, even like the Declaration of Independence, people are so sensitive about the humidity conditions, you know, whether you've got filtered light coming in,
yes,
not just bright light or fluorescent
yes,
lights. And they're really almost paranoid about the thing. And it comes as a real surprise to me that they would go into this huge facility, yes, with an intense, brilliant X-ray, yes, beam a billion times. How did you ever convince them? Besides the parchment test, yes, I mean, that could be a trick. Right, you know? Yeah. How did you convince them that it would be safe?
Let me first of all, the thing which really caused me the most headache in this whole project was actually the humidity and the temperature. We could have bought air conditioning system which was way too expensive that I would have gotten funding for it. And so we came up, I had a student at the time, we came up with a really, we went to Sears, bought a $100 humidifier, but when you really measure the humidity, it's like a cowtail. It goes like 44% to 56 and then shuts off, then it drops down to 44. So we came up with building a tent where we let it leak out to damp that oscillations. And so we got it to 50 plus minus 2% and like hovering there. So that was the humidity. Temperature was easy because the synchrotron is air conditioned. So that made that was fine. The X-ray, when you talk to anyone about X-ray fluorescence imaging, right, in particular commercial people, they always say it's a non-invasive probe and it's non-destructive. It's not true. I mean, we all know that it's destructive, and that's why we don't get a chest X-ray every day. But you can measure the damage of X-rays to anything. And we, doing the work on the spinach, we are extremely sensitive to radiation damage. And because we can see it very much, and it destroys our data. So I had already some background of being careful with samples. In that case, it was for a different reason. So what we did is, we said, before I even said to them, send out, let's do some tests. So we did some tests with some newer parchment. And then not only did we visually inspect it, but we sent it to a lab in Ottawa where they took it apart and looked at the fibers. And they could establish what is called a characteristic temperature. So in other words, they compared the fibers, because the fibers start to shrink when you put X-rays on, they start to dry out. And they compared it to what happens to the parchment when you put it in a certain temperature. And so they have established that if we take a certain dose of X-rays, there is no effect. And then when you go 10 times higher, you start to see as if it starts to warm up. And that was the result which we then sent to the Walters Art Museum. And the rest is that, of course, they had to have some confidence that I don't just lie to them. But what we really did during the imaging, we used a dose which was about 100 times less than the safe, 10 to 100 times less than the safe image. So I'm not worried that in 100 years, all of a sudden, those X-ray pages will fall apart. I don't think we did any damage to them.
Okay. Henry Mittler, you get the last question.
Okay. I was intrigued by your comment about the well-known effect of spinach on water, which I don't know.
Oh, no, it's not, yeah.
Could you explain it, please?
Well, yeah, maybe I didn't express myself clearly. The reason why we study spinach is, the most important catalytic reaction on Earth, arguably, is the splitting of water to oxygen done by plants and cyanobacteria. This process started about 3.8 billion years ago, at a time when the atmosphere had no oxygen. It was literally all reducing methane and CO2, etc. And it slowly enriched the atmosphere with oxygen. And then only 3 billion years later, at the beginning of the Cambrian explosion, the level of oxygen was high enough to sustain more complex life forms, such as trees and animals, etc. And everything started from that. It is that reaction, 2 water molecules in, an O2 molecule out, and of course there's CO2 in as well and carbohydrates out. It is that reaction which is done by a little manganese cluster made out of 4 manganese atoms and a calcium atom. It's a little catalyst. It happens in every leaf. It happens in cyanobacteria. And spinach, because it is pretty soft, is one of the materials where you can concentrate this manganese cluster in a high form. And my colleagues from Berkeley and we use X-ray spectroscopy to try to find out how does this process work. It's one of the few, or it's one of the many big unsolved mysteries. How exactly is the water brought in and the oxygen spit out? So we have, there are literally dozens of groups who apply different techniques to look at this process, and that's the technique. X-ray fluorescence spectroscopy and X-ray absorption spectroscopy is a technique which I have worked on for 10 years now to look at this process. Right? And it is the manganese. So we don't look at the iron, we look at the manganese, but there is about 3 times more iron in spinach as well. If you know that according to Popeye, there's tons of iron in spinach, which is actually wrong. That was one of those factor 10 errors, which was never corrected. So we all grew up eating spinach, which is fine. It's not bad, but it doesn't have as much iron as a lot of people think.
Thank you, Uwe. Thanks for giving us an excellent talk today. I wanted to ask you, funding agencies love this stuff, or do they say, well, it's not real science? Thanks.
They